Hi everyone, I welcome you all in the next lecture of ethanol production. So in previous lecture, we have seen that the method of production of ethanol, and we have already seen that there are various steps where you can see one common thing, that is the ethanol that is from petrol pump to sugarcane field to medical bottle or medicine bottle to the beer bottle. Only one thing is common, that is the ethanol. And then we have looked about there are two options of the fuels right now. I'm not talking about the diesel. I'll only compare about the petrol and ethanol. That's why I have already discussed what there are two options of fuels, that is petrol and ethanol. And then we have also seen that what is difference between the gasoline, that we call it as a petrol, and ethanol, based on some physical and chemical properties of gasoline and ethanol. And then we have looked about how basically this ethanol production takes place in the plant. And I mean, what are the feeds? So that, like, here we have seen that molasses and water was the feed for the ethanol production. And then we have seen various unit operation and unit processes that is involved in the production of ethanol from the molasses. And then we have also looked about what is the molasses, and why does sugarcane need so much amount of the water. And then we have seen that in order to produce per hectare of the sugarcane, you require basically 15 to 25 million liter of water. That is itself is a huge quantity. And then we have also seen that why India is having huge potential for producing sugarcane, and that basically serves as one of the best feedstock for the or one of the potential feedstock for the production of ethanol. And then we have seen that why molasses is used for the ethanol production, and how basically the ethanol is being produced inside the plant using the using yeast. And then we have also seen that some results from this paper that has been published in 2006. And also we have, I mean, I have also answered about various questions like why do we blend ethanol with the petrol? And then if ethanol has lower energy than petrol, why are the countries blending it into the petrol, and whether it is actually beneficial or not? And I have discussed the results from this paper, which is approximate results, right? Then we have also seen that how we can calculate the energy of the blended fuels like E10, E20, and E50. And then we have compared the energy of all of these fuels. And then we have also seen what is the mileage, and whether the mileage is just only energy available for 1 liter of the fuel, or it also depends upon another parameter, that is engine efficiency. So if you are having good engine or engine efficiency is more, you can increase the mileage. And in today's lecture, we'll see. There is another interesting thing, and that is very important to understand when we talk about energy efficient engine efficiency for petrol engine as well as for ethanol engine. And at the end of this lecture, you will appreciate that you will be able to answer various questions like whether why octane number for the ethanol is more compared to the petrol, and if there is a high octane number, which if fuel is having higher octane number, then that fuel is good or not, and what is basically the octane number is, and how you calculate the octane number. And then we'll also understand that why you know ethanol engine or engine having higher octane number is more efficient, right? So here I'll start with the engines knocking. So in order to understand the engine's knocking, so knocking is just kind of noise. So engine creates some kind of noise, and in day-to-day life we listen that kind of noise that is coming from the engine. So we are going to understand why this knocking is happening. So when if you see here, there is a no engine. So in this engine, basically, uh, the fuel and air mixture, enters into the engine first, and then what happens? This piston basically compresses this fuel and air mixture, right? And once this piston compress this fuel and this mixer, then at a particular time what happens, at a particular compression ratio, this spark plug basically inject the spark, and this fuel and air mixture will start burning. And after burning, what will happen? The second stage, this vapor which is being created or which is being formed after the spark ignition here, then this will push the piston outside, and through which the crank will move, and no vehicle movement will take place. So the basic thing of this particular uh, uh, image is that first the air fuel mixture enters into the engine, and then this piston compresses this at a particular compression ratio. This spark plug produces the spark and the ignition takes place. So this is for the normal combustion engine. But sometimes what happens, if fuel is not good or having some different issue with the fuel, as I'll tell you what is difference between the petrol and ethanol, and why pre-ignition takes place in case of petrol, not in case of ethanol. So let's say if I talk about the petrol. So once you compress the petrol air mixture in this piston, in this engine, then what happens? There is a pre-ignition, because petrol is a mixture of various hydrocarbons, and hydrocarbons are connected with weak van der Waals forces or London dispersion forces. And if you compress the piston more, then what will happen? The petrol molecules will get disintegrated or detached from each other, and that will create a large number of free radicals. And what happens? This large number of free radical, if you compress that free radical before a spark plug, producing some kind of a spark, it will, create that free radical basically gets auto ignited, and due to this particular reason, it will ignite the fuel. So it just don't won't wait for the suitable time where the uh, fuel air mixture will get ignited. So it will create some pre-ignition. And then due to this pre-ignition, what happens? There will be, some spark due to the pre-ignition, and then there will be a spark that is being generated at the, due to the auto ignition kind, when this spark plug will generate the spark. And now both of these spark will collide, and that will create some kind of vibration. And that is a kind of vibration that we listen as a noise. So this is called as the knocking. So now you would have understood that why knocking occurs. So knocking occurs due to the pre-ignition of the fuel, and that basically occurs for the petrol, because petrol is connected with petrol molecules, like contains various hydrocarbons, and all of these hydrocarbons are connected with weak hydrogen bonded, that is a weak van der Waals forces of attraction, or weak London and dispersion forces. And due to this particular reason, if you compress this more, then what will happen? At the higher compression, the molecules, hydrocarbon molecules will get disintegrated into the free radical, and due to that compression, that free radical molecules will generate some kind of heat, or it get ignited, and that is called as the pre-ignition. And this pre-ignition, during the pre-ignition, what will happen? These both of these spark molecules, collide with each other inside the cylinder piston assembly inside the engine, and then this creates some kind of vibration, and that is called as the noise. That is also called as the detonation in technical term. And this is called as the, I mean, this is all about the engines knocking. So now how to, quantify the knocking, that if knocking is happening, then there may be, you would have listened that there will be some engine making more noise, some engine is making less noise. So how you can quantify the knocking? So in order to, quantify the knocking, a parameter that is known as the octane number has been defined. So octane number basically tells you the measure of how resistance of fuel is about auto ignition during the compression. So if octane number is more, then that means fuels are having higher resistance for the auto ignition. It won't get auto ignited. And if fuels are having lower octane number, then it will get auto ignited very easily, and then that will create more noise. That is called as the knocking. So if we compare the results of fuels having different fuels with different octane number, so regular petrol that we basically use having octane number is 91 to 95 octane number, that is very prone to the knocking. Then there comes a premium petrol having octane number is 97 to 100, that will resist the knocking. And then the ethanol, that is the discussion topic of this lecture basically. So having octane number is 108 to 109. So ethanol is having extraordinary anti-knocking characteristics, right? So this is one of the best property of the ethanol that can become a good fuel. So this plot basically tells you that octane number on the y-axis and the various fuels on the x-axis. This is just a graphical representation of the octane number of all of these fuels. So I hope this engine knocking is very clear to all of you now. Now coming to the next part of this discussion, that is how is octane number calculated, right? That is very important to understand, and then you will be able to answer different kind of methods of measuring the octane number as well. So as I have told you, octane number measures how resistance a fuel is to the autoignition during the compression. So in order to understand this octane number, first there are two fuels, that is isooctane and heptane. So isooctane is having octane number 100, that is a reference fuel, because if you burn this fuel inside the engine, or if you put this fuel inside the engine and if you start the engine, that will not create any kind of noise, and that's why it has been assumed as a reference fluid. And when we talk about N-heptane, if you put this fuel inside the engine and if you start the engine, it will create huge noise. So scientists has taken these two fuels as a reference fuel for, you know, reference fuel for the octane number. And for isooctane, it has been assumed that octane number is 100. And for N-octane, it has been assumed that the octane number is only 0. Now, in order to test this octane number, there is a test engine that is called as the CFR engine, that is also called as the Cooperative Fuel Research Engine. So in this engine, basically what happens, this single cylinder, will be a single cylinder, and then there will be variable compression ratio. So as I have told you, once the air and fuel mixer enters into the engine, then what will happen? That piston basically compress that, and then we define a compression ratio that you will see in the next slide. So there will be a single cylinder variable compression ratio in this CFR engine, and then the composition ratio of the fuels can be changed. That actually, let's say if you are mixing two fuels like isooctane and heptane, and then you can change the fuel ratio like 10 is to 90, 20 is to 80, 60 is to 40, something like that. And then you detect the knocking, right, using a knocking sensor, and then based on the engine speed or temperature and another condition that you will fix here. So basically what is happening at different fuel ratio, you are, measuring the knocking of the fuels using the knocking sensor. And then there is a octane number scale that has been defined from 0 to 100. As I have told you, 0 is defined for the N-heptane, that is having very poor knocking resistance, and for isooctane, that is having very excellent knocking resistance, that is 100. So any fuel that behaves as a mixer that contains X% of isooctane and 100 minus X% of N-heptane, and that is assigned as an octane number of X. So if X% is, let's say, 95% of octane and heptane, sorry, 95% of octane and 5% of N-heptane, then that fuel will be having 95 octane number, right? So you will see here how this is basically calculated. So what happens, let's say you have an unknown fuel and you run that fuel inside a CFR engine that I have already explained you. And now you increase the compression ratio until the knocking starts. So let's say now the knocking starts at a compression ratio of 10 is to 2. Then what happens? Prepare a mixture of isooctane and N-heptane. And then what happens? What make different, mixture with known percentage of isooctane and N-heptane. So let's say you start with 100, 0, then 90, 10, 20, 80, all of these things, right? And after that, what happens? Run each mixture, whatever you have prepared using isooctane and N-heptane in the CFR engine, and let's say find the mixture that given the same knocking intensity at the same compression ratio of 10 is to 2. That is for the unknown fuel. And this is how you perform the experiment in a lab. And then you, for both of these cases, you measure the knocking using the sensor. And then if you got the match for the same knocking, at what ratio it is making the same noise for the isooctane and N-heptane, and for a non-fuel. So that percentage of isooctane, let's say it is 60% or 80%, that percentage of isooctane is 80%, then that will be the octane number for the unknown fuel. And this is how scientists measures the octane number for the unknown fuel, right? I hope this is clear to all of you how octane number is being measured in the laboratory. So to define the octane number, there are two definition of the octane number. That is the research octane number, that is called as the RON, and then there is a motor octane number that is called as the MON. When we talk about the research octane number, that is measured at a light load, that is low engine speed and the mild condition. And basically RON is in India, basically if you see any octane number on the petrol pump, that research octane number, they display basically the research octane number RON. When we talk about the motor octane number, MON, that basically measured under high load condition, and you know that should be high engine speed. I'm really sorry for that. That should be high engine speed and the high temperature. That is adverse condition, right? Now, that is all about the octane number. Right. So I'll stop this lecture here because if I'll move towards the next topic, that will become more complicated for one lecture. So the goal is to let you understand each and every topic very clearly so that at the end of the lecture, you will be able to answer or you will be able to understand why ethanol, which is better fuel, whether ethanol is better fuel or petrol is better fuel, or the blend of this mixture fuel like E10, E20, E30 is a better fuel, and why this is the better fuel. So that is the goal of this lecture series. So I'll stop this lecture here. In the next lecture, we'll start with the new question. That is, why does ethanol have such a higher octane number, right? That is very interesting topic, very interesting question. And you will be at the end of that next lecture, you will be able to answer this question. Okay. Thank you. See you in the next lecture.